Alright, so we're on page 7 of the Unit P packet. We're looking at eliminating the angle parameter. It's a continuation of what we did on page 6. So there's a lot of familiarity that's going to take place here. We're relying on just prior knowledge related to trigonometry. Right? One of those key ingredients would be the fact that cosine squared theta plus sine squared theta is equal to 1, all right, the Pythagorean identity. Now, we have here x is equal to 3 times the cosine of theta, but that can be thought of as cosine of theta is equal to x over 3. Same idea for the y equation. That could be thought of as sine of theta is equal to y over 4. All right, so instead of saying cosine squared, I can say x over 3 squared. Instead of sine squared, I could say y over 4 squared. And the whole shibiggity bangity boomity boom here would be equal to 1. All right, so if I simplify, x squared over 9 plus y squared over 16, that's a very familiar looking, hopefully, familiar looking conic section. However, if you're not comfortable with that, you can type in your original parametric 3 cosine, but use t instead of theta, comma, it always goes in as an ordered pair. All right, you put an ordered pair in as a function. All right, so it's a vector valued function basically. All right, if that term doesn't seem familiar to you, that's okay. That's one of the things that we're going to cover in this course. So you're not behind the curve if you don't know what that term vector value function means. It's one of the reasons why you're here. All right, and you look at this and say, well, this doesn't look like a conic section. You're a liar. And I say, well, hold on, time out. 0 to 1? No, 0 to 2 pi. The default setting on Desmos is 0 to 1. All right? It has to be a default setting of something, so why not be 0 to 1? Desmos doesn't assume that you're, just because you're putting in a trig function, that you're working with unit circle related values, or a particular domain. All right. Now, that's all well and good. It's a good looking ellipse, suppose, but we want to make sure that what we got was correct. So I type in x squared over 9. I mean, you could kind of verify it just by visual inspection, but we want Desmos to do the work for us, at least in this instance. All right, so you can see here that I'll just turn them off. You can toggle on and off by tapping on the icon on the left hand side of each line of code is a generous term, but each input field. So turn on, turn off, turn on, turn off, turn on, turn on, turn off, turn off. You get the idea. All right. So we're good to go there. Now, for the second one, x is equal to cosine 2 theta and y is equal to sine of 2 theta. It's the same relationship. Right? Cosine of theta plus sine, cosine squared theta plus sine squared theta is equal to 1. True, but also cosine squared 2 theta plus sine squared 2 theta is equal to 1. And that's because cosine squared of any argument, so any angle, plus sine squared of that same angle, it still follows the Pythagorean identity. All right. So if you're unsure, you can check cosine. Now it's a little iffy with the way Desmos understands it. You type it in, but it builds in the parentheses, so you have to kind of retroactively go in and put the words are escaping me. The power of 2. So backspace, pop it in there. I'll pop in a 2x. All right. Now, If that doesn't look like the line y equals 1, I don't know what does. All right. So if you're unsure, you just type in a 1. I'm sorry, y equals, geez Louise, it's going to be an equation. Equals, I said, y equals 1. All right, so 1, and I'll write this as a function even though it knows it's a function. Y equals, instead of two graphs, they should be equivalent. On, off, on, off. Alright, map into the same location, so we have equivalence. Alright, so that tells me that I can just swap out, instead of cosine 2 theta squared, I can just say x squared. Oh, that is not a marker. X squared plus y squared, result would be equal to 1. Alright, so that's the unit circle. Alright, so let's investigate, shall we? Alright, so we know that, and let's just wipe all this out, that we can type in parametrics as ordered pairs, so 2t, comma, sine of 2t, alright, fragment of a circle, that's okay. Pop in the 2 pi, and that looks like a circle with a radius of 1, centered at 0, 0. Alright, now it's kind of interesting because if you play around with the domain, you get different portions of the circle. Alright, so let's say I only went to pi. Only going to pi actually gives me a full turn around the circle. And you'd say, well, what about going to pi over 2? Half of a circle. So normally it would take 2 pi radians to get all the way around a unit circle, but that's when the argument is theta. Here the argument is 2 theta. Right? So that's because the frequency is 2. That means we're getting 2 full cycles in that 2 pi period. Right? So if we were to actually graph out, the ordinary cosine graph and the sine graph, separately. Right? So we'll have to account for that when it comes to finding some of the solutions to the calculus applications of this stuff. But for now, we just have to be mindful of the fact that the domain may be more than sufficient, whatever they're giving us. But what they're telling us here is that, okay, we have a circle. Oh, they didn't ask us to draw it, but I'm going to do it anyway. I always say they, as if I wasn't the one who made this. Right, so what they're saying here is that we started at this location, we traveled around the circle. Alright, that was pi radians. Alright, then we basically went a second lap. Alright. That got us to 2 pi. Alright. So you just got to be mindful of the fact that sometimes the road and how far you've traveled are not necessarily the same thing. Like there's the lap, like think of it as a track, behind a school or something, and somebody's running laps on the track. Okay, so do they just go around once and stop because the track is just one lap? No, they can keep running around the track. And it's kind of funny, you wouldn't see this, but I'm gesturing in the air as if you can see my hand movements. But I mean, that's the idea, is that the pathway is there. How you travel along it is also relevant information, and we need to investigate that. And that's going to be a recurring theme in the course. Right, so then for number 8, we get into general terms. Number 9 is hyperbolic functions, which is sort of beyond the scope of the course, but I like to talk about it anyway, just because it doesn't really behoove us to ignore hyperbolas completely, even though they say we shouldn't, or we don't have to cover hyperbolic trig functions. I mean, I'm not going to test you on it, but it's good to learn it. All right. So a cosine of t, b sine of t. Right? The idea here is that we can generalize, and then maybe, just maybe, going forward, you can recognize what kind of function you're dealing with just based off of the parametrics without ever having to go into rectangular form. All right? So we know that cosine, again, squared plus sine squared is equal to 1. All right? So cosine of t is equal to x over a. Sine of t is equal to y over b. All right, if we know that cosine squared t plus sine squared t is equal to 1, then I'm really saying that x over a, the quantity squared, plus y over b, the quantity squared, is equal to 1, which in turn tells us that x squared over a squared plus y squared over b squared is equal to 1. All right, so just by knowing the coefficients of cosine and sine in parametrics, we could actually represent a conic section, specifically an ellipse. All right, so let's investigate, shall we? So I'm going to do this. I'm going to get a little cute here. I'm going to put the A in. I'm going to put the B in. It asks me if I want to add sliders. I sure do. All right, and then, but I'm also going to get even cuter. So our domain can go from 0 to whatever. Right? It actually can go from negative whatever to whatever. So why don't we do that? Negative, let's say D for domain. So I can work off of absolute values and then play around with the domain from there. I could also just kind of, develop the framework of it. If I want to go from, let's say I want to go from negative, well, it's a circular function, so let's say I want to go from negative 4 pi to 4 pi, but I want to do it in pi over 6, I'll do pi over 12 increments. It's going to give decimal values, but that's going to be the step. All right, so when I move things around, it's only going to go in pi over 12 increments. All right, now maybe you only want to go from 0 to D. That's fine too. But what I'm looking at here is a circle that's generating in both directions because I'm expanding outward in the direction of negative D and also in the direction of positive D. All right. So it gives me a sense of how far I need to go before I cover one loop. So that's telling me that I'd have to go from negative, well, it kind of moved off of my, this is the fat finger syndrome. But if I can get it to stay put, which it doesn't always want to do. Come on. There we go. It's telling me that in order to get one full turn around this circle, I just go from negative pi to pi. All right. Now, if you want to go and make this a 0, that's fine, just to make it, a little bit more comfortable. Something a little bit more familiar. Then you see that you would need to go out, in order to get one full turn, you need to go out to 2 pi. All right. Either way. But also, as you can see, if I manipulate my A value, it gets wider. My B value, it gets taller, so I'm making an ellipse. But then look what happens. Let's say I make the B value a 3, if it'll stay on a 3, and my A value, let's say I make that a negative 6. You see, so I said, look what happens. It's look what happens, and what I mean by that is look what doesn't happen. it's telling us, we learned from this, that the positive or negative a value is not going to impact the type of conic, because we're squaring it anyway as part of the standard form, but it will impact, if we go back to 0 here, it will impact how the graph is generated. So if I start this off at 0, and let's say I want my domain always to start at 0, I can just change my low bound so that's the case. Then when I advance it beyond 0, see what's happening here is that it's moving in a clockwise direction. It's still going to take 2 pi in order to make one full loop, but it did it in a different way. It basically ended up being a reversal of what the original conic would have been, right? So we're starting, instead of at 0 degrees, we're starting at 180 degrees, and instead of going counterclockwise, we're going clockwise, right? So it's basically a mirror universe, you know. So it's something that you can learn from creating a script on Desmos that maybe you wouldn't necessarily get from a TI calculator, and also you wouldn't get by doing it by hand. All right, now as far as the hyperbolic function is concerned, or hyperbolic trig functions, there's some hyperbolic rule. There's a lot of hyperbolic rules, but one of them is that cosine squared, I forgot the H, cosine squared, hyperbolic cosine squared of t minus hyperbolic sine squared of t is equal to 1. All right, and I'll get to why that's the case in a second. It actually has everything to do with simple the unit hyperbola relationships, but more on that in a minute. All right, so the relationship here is that cosine as a hyperbolic function, cosh is what I've, my teacher back in the day called it cosh, and that sounded good to me, so that's what I went with. But then he called the other one cinch, and I was like, all right, not loving it, but it's better than saying sin. So we just did it, we just lived with it. All right, so we're looking at x over a squared minus y over b squared equals 1, which corresponds to x squared over a squared minus y squared over b squared is equal to 1. And that's the equation of a hyperbola centered at 0, 0. Now, if you want the unit hyperbola, we'll just kind of talk about that for a second. The unit, you know how we have a unit circle, we have a unit hyperbola. All right, so, and actually let me take a step back and talk about the unit circle for a second, and the standard form for that. Unit circle, we actually have it written here on the paper already, if you want to call this paper. X squared plus y squared is equal to 1. All right, so x squared plus y squared. And if you think about the standard form for an ellipse, standard form for a circle, we have the plus sign separating the x and the y's. For a hyperbola, we have a minus sign separating. So the unit hyperbola is x squared minus y squared is equal to 1. All right. So if I'm just going to turn all this stuff off, but let me just pop that in real quick. X squared minus y squared is equal to 1. That is certainly a hyperbola, but let me show you the unit circle also. Little copy paste action. Make that a plus, and you can see that this is just basically the inversion of the circle. If you were to just kind of if you're thinking of it as a form of magnetism, you know, like the opposite poles attract and then the same poles repel, that this is kind of what's happening. Everything that falls in the unit circle would be the opposite poles attracting, and anything outside of the circle or within the hyperbola would be the effect of the like poles repelling. All right. So if we know that x can be thought of in the unit circle or the unit hyperbola as cosine, x is equal to cosine of theta, y is equal to the sine of theta, then we'd have cosine squared theta minus sine squared theta is equal to 1. All right. So, but that's an issue because that would actually be on a unit circle. All right. So what we do is we invent this brand new notation and say, okay, well, that's not going to fly because that's going to give us incorrect relationships. And in fact, you can verify that. All right. I can tell you, and I'll show you. Showing is going to be better than telling. Cosine squared, I'll go with x, minus sine squared, same deal, x, all right, let me turn off all this other stuff. You take a look at that. There's a lot of things you can glean from this, but one thing you're not going to get is you're not going to look at that and say, well, that's clearly a hyperbola. And that has to do with the Pythagorean identities, because you could swap out, for example, the cosine squared and replace that with a 1 minus sine squared, simplify, and you'd end up with just an oscillating trig function of one variable and one trig function. Right? So what we do is we kind of morph it over and we say, all right, we're living in the world of the unit hyperbola. So we have trig functions specific to that. Right? So it's kind of like a new universe. So we would say x is equal to the hyperbolic cosine of theta, and y would be equal to the hyperbolic sine of theta. So what would happen is, instead of having this, which is really a trigonometric identity, it's actually a double angle identity for cosine, you would have cosh squared theta minus sinh squared theta is equal to 1. All right, I'm just going to smidge this stuff over real quick. All right, so that would give us a relation involving the unit hyperbola, and that would be basically your equivalent to, or your analog to, the Pythagorean identity. All right, so that's one of the things that we can rely on. Now, as far as, I mean, that's probably more information than you were expecting, but it's valuable and useful, and again, it's beyond the scope of the course, but it's stuff that why not? It does have ties into what we're doing, even though we won't tackle it directly. All right, so I'm putting in A and B. Put it over a reasonable domain. I'll go 2 pi. Oh, actually, I'll just go D, because it can still call back on the D from before. All right, so it does give us part of that hyperbola. It's just not giving us the whole thing. All right, so we want to get some more D in there, more domain. See what it does. say we go, I'll actually leave it at, I won't even go in terms of pi, I'll just go get some big numbers in there, going by ones. Alright, so let me get some coefficients, make them both positive, and so depending on whether they're both positive, one of them's negative, the other's they're both negative, or one of them's positive, one of them's negative, it gives you a different piece of the hyperbola. So you get what you need, it's just maybe not in the way that you're expecting. All right. So then the actual function, or the equation I should say, x squared over a squared minus y squared over b squared is equal to 1. So you see you get the whole thing all in one shot, whereas the parametric, depending on where you're living, you know, it's kind of hard to see, but there's a little bit of it that's darker. Everything along this path is a little darker. That's because the red and the blue are supposed to come together to make a shade of purple. It's a little off, but we're kind of living down here. But if I move my values around a little bit, it tweaks it. All right, but and that's a little bit of a taste of hyperbolic trig functions, but that's pretty much where we're going to leave that. All right. Now, if you need to convert from rectangular to parametric form, it's actually a whole lot easier, because we have to actually make an assumption. Unless you're actually given a relation, you have to make an assumption about what the value of t would be. So we have y equals x squared plus 2x, and we want to convert it into parametric form, but they have to tell us something about how t relates to either x or y. Okay, so here they're telling us that t is equal to x. Okay, great. So that means that I can substitute into my equation everywhere I have an x, I can replace it with a t. So that would mean y is equal to, instead of x squared, it would be t squared plus 2t. All right, so my parametric equations can be written in a few different ways. One way would be to say x is equal to t, that was given, while y is equal to t squared plus 2t. Or you can write it as an ordered pair, t comma t squared plus 2t. As long as you put the x first, you're fine. All right, very easy to check. I'm just going to get rid of all this stuff. We don't need it. Type in your original, y equals x squared plus 2x. That's what the original parabola looks like if I put in the ordered pair using t's, t comma t squared plus 2t. Close them up. Again, we're always going to have that domain issue, so I'll say like negative 10 to 10. You see it's piecing it all together. Alright, so 1, 2, same graph. Alright, now they tell us here in the second part that t is equal to x over 2. Alright, same deal, but this time I need to solve for x first. X is equal to 2t. But it's the same idea. If I know that x is equal now to 2t, then I can relate, or, well, it's still a relation, but I can replace, is what I meant to say, the x's with 2t's. So y would be equal to 4t squared plus 4t. So my answer here would be, it's twofold, the same as before. We can represent it one of two ways. I could say x is equal to 2t, while y is equal to 4t squared plus 4t. Or I could say 2t comma 4t squared plus 4t. Alright. So you know what I'll do is I'll just pop it in here. 2t 4t squared and 4t. And I take a look at the graph, and it's the same graph. And again, it's the question of the road versus how you travel along the road. The issue here is, t is equal to x over 2, x is equal to 2t. It's giving us a sense of how t relates to x. Right? Is t moving really essentially in lockstep with x? If t represents time and saying, and x, let's say, is a horizontal, foot traveled in a horizontal direction, then can I say that for every horizontal foot traveled, 1 second will elapse, as opposed to for every horizontal step traveled, 2 seconds will elapse. Right? So it means you're going half the speed. Right? So you're going slower. Right, that's all that's happening here. Right, and so you can kind of get a sense of that. Again, just playing around with the domain. Let's say 0, and we'll go with D again. Add the slider. And then just animate that slider. I'll start it off at 0 to make it a little bit more user friendly for Desmos, and actually it doesn't even have to start at 0. I can make it whatever, but let's say we're starting at 0 and go into like 100. So I can animate that, starting at 0, animate it, goes pretty quick, but then I can duplicate it and just go back to the original form. So this was a t squared and a 2t. Again, quick animation. Look at them one at a time instead of simultaneously. And just try to get an eyeball, just a sense. I'll turn off the original. Versus this one. It's still going pretty quick, but yeah, depending on how you set your animation, you might get a sense of whether or not it's going a lot faster or a lot slower. This one it's almost imperceptible, and it's a little tougher to see. In this case, subtracting 1 from both sides, x is equal to t minus 1. Substitution, y would be equal to t minus 1 squared plus 2 times t minus 1. There really isn't much value in simplifying this. So what we can say is x is equal to t minus 1. Y is equal to, feel free to simplify whenever you want, just at your own peril. Because if I don't ask you to simplify something, and you take it upon yourself to simplify, and you screw it up, you're on the hook. All right? Anything on a test paper that you write down that's incorrect, whether it's relevant or not, could cost you points. So don't simplify unless you're directly told to. All right, so these would be the two ways that you can represent your answer here. All right. So again, you can play around with this and throw some animations in, see what's going on. Go to minus 1. Minus 1 squared. And then 2t minus 1. And just have a look. You know, and it could just be a matter of, you know, dialing down the value, or maybe you only want to go to like 5 and have it go in like really, really tiny steps. And see what's going on. Alright, that'll make it go slower so that if there is a relationship, you might be able to see what that relationship is. Alright, so I'm looking at this one. Alright, I get an idea how fast that is. Does this one seem faster or slower? I don't know. It feels like it's going a little slower. Alright. So you can kind of you play around with the animation function and see if it